Sutter. I'm a professor at Whitman College, and I'm going to be telling y'all about my work looking at the fraction of dust that's in the form of PAHs using JWST photometry for 19 nearby galaxies. Now, before I get into what I did for this paper, I should probably explain what a PAH is. So a PAH is a molecule of a polycyclic aromatic hydrocarbon. So it's a chain of hydrogen and carbon that we see a lot of in the interstellar medium. Astronomers think of these as the smallest dust grains, and they play a lot of really important roles when we think about how the ISM heats up, how the interstellar medium heats up, how larger molecules, CO, H2, form within the ISM. So a lot of important roles for ISM chemistry. And they also play roles in the ionization balance. And this is because they have a lot of electrons that can be photoejected by light from young stars, and that can change kind of the balance of positive and negative charges in the ISM. They also produce a lot of the infrared emission that we see coming from galaxies, up to 20% of the total infrared emission, and they do this by kind of wiggling around. So when these PAH molecules wiggle or rotate, they produce emission in the near and mid-infrared, and we can observe these with JWST. They're very bright. They produce a lot of that infrared emission, making them observable even in the high redshift universe. And so they're these very important, very easy to detect molecules that we see in the interstellar medium. JWST is really well suited to study PAHs because a lot of the photometric bands on JWST cover the most prominent PAH emission features. So this is a model showing dust emission from a couple of Drain et al. Models of dust emission, with the photometric bands NIRCam and MIRI highlighted by different colors. This is from the Chastney et al. Paper that came out in 2023. And what we can see is that some of the biggest bumps here, the biggest emission features from the PAHs, where the y-axis goes highest, are really well covered by our NIRCam F335M, as well as the MIRI F770, F1130, and F1130 filters. As part of this project, we also use some of the filters that don't cover PAH emissions. So specifically, I'm going to highlight that F2100 emission filter. It's kind of the brown line there, and it's showing up in a place where there isn't a bump, but there still is that continuum emission. So we're going to use that to trace larger dust grains. Now, when we study PAH emission, what we would really love is to have spectroscopy so we can individually measure all of these emission features. But spectroscopy tends to be really observationally costly because of both the small field of view and also just the longer integration times it takes to actually produce good signal-to-noise ratios on spectra. So what we were hoping is that we could measure the PAH emission using only JWST photometry and trace the distribution of PAHs with just these photometric measurements. To do this, we first have to do a little bit of work. We're going to focus on those MIRI bands and not so much the NIRCam band, because the NIRCam bands are a little bit more complicated. But in the MIRI bands, we do expect most of the light we see to be coming from PAHs in most situations. But there are some specific ISM contexts where there might be a fair amount of starlight sneaking into our F770 wide filter especially. So before we use F770 to trace PAHs, we first do a star subtraction. So what this figure is showing here is a couple typical models for galaxy emission made using the Seagal program. In both of these, the black lines are the total emission we would observe, where the red lines are emission from dust. Both of these models use the same starlight emission model, so we see that purple line here is the unattenuated starlight, and it's the same for both models. With these two models, the difference is that one of them has a high percentage of PAHs, or a high QPAH, a high PAH fraction. It's a solid line. The other one has a low QPAH, so a low amount of PAHs, and that's the dashed line. And what we can see with the solid line, the red line and the black line are basically overlapping at 7.7 microns. So that means all of the emission we're seeing at that wavelength is from the PAHs, is from the dust and the PAHs, I should say. Whereas in the dashed line, where there's that low PAH fraction, blue line, the blue purpley line, and the red dashed line are about equal on the y-axis at 7.7 microns, which tells us about 50% of our emission is coming from stars and 50% is coming from dust. So in situations like that, we want to make sure we're removing that starlight, so we're not counting something as having a lot of PAHs when it really has a low amount of PAHs but a lot of starlight. So in order to remove starlight, we use a band where we know most of the emission we see is going to be coming from stars. And this is one of our near-cam bands, the f200 wide filter. This is at 2 microns. At 2 microns, there shouldn't be any PAH emission. We should really only be seeing light from stars. So we can use that filter as kind of a baseline for the amount of starlight we expect to see in a certain spot in our galaxy. Using a bunch of emission models for galaxies, we can then predict the relative amount of starlight in the f770 wideband based on how bright the f200 wideband is, and we can kind of scale f200, remove that from the f770, and be left with our star-subtracted f770 light, where we expect all of the light in f770 to be coming from those PAHs, or at least all of it to be coming from dust. We haven't done anything to subtract dust continuum, so there is still the possibility that some of our larger silicate and graphite grains or silicate and carbonaceous grains are emitting continuum in our band, but at least we know we're not picking up on stars. So once we have our f770 with the starlight subtracted, we can start going about looking for PAHs and where the PAHs are in our sample of galaxies. For this work, I focused on the 19 galaxies included in the PHANGS-JWST Cycle 1 program. They're all shown here. These are all nearby galaxies, so distance is less than about 20 megaparsecs. They're all pretty close to face-on, and they're pretty much all star-forming spiral galaxies. Now we do have some irregular galaxies like NGC 5068, some barred spirals like NGC 1300 and NGC 1512, and even one galaxy that we know is an AGN, so NGC 1365, as well as a few others that are believed to host AGNs. We have a wide range of galaxies even within these first 19. With all this data, we can now go about defining our tracer of the PAH fraction, our photometric tracer of the PAH fraction, which we're going to call our PA. Our PA is just the sum of our two MIRI PAH tracing bands divided by our dust continuum band. So just as a reminder, I've shown that dust model again where we can see the purple and the yellow are our F770 and our F1130, and then our PAH tracing MIRI bands. And then the red is our kind of reddish brown is our dust continuum band, the F2100. So what essentially we've got with our PA is PAH emission normalized by dust continuum emission. We're hoping that this is similar to the QPA value that I showed earlier, value that gives us a fraction of the dust that is in the form of PAHs and is based on one of the parameters from the Drain et al. Dust models. So in order to test this, we wanted to compare our measurements of our PA to measurements of QPA in galaxies where we had a really nice model of the dust from the Chastanet et al. 2024 dust models, where they looked at actually making dust models with far infrared data as well. Now these were much lower resolution and not all of our galaxies had these dust maps, so we could only do it for the 7 shown here, but what we do find is that there's a pretty nice linear relationship between our PA on our y-axis and QPA on our x-axis, and that it seems to hold true basically the same relation for all 7 galaxies. Now, one of these galaxies is an outlier, that's NGC 1365. It looks a bit funky. We think that's probably because of that AGN in the center that also saturated the nucleus, and we had to remove a lot of the data from that galaxy. So that one maybe isn't quite a nice linear relationship like the other 6, but the rest of them look pretty good and tell us that our PA is tracing QPA for a kind of typical range of QPA values that we would expect in the ISM. So now that we know that our PA does seem to be tracing the fraction of dust in the form of PAHs, we can start to look for where our PA changes across our sample of 19. So this is just one example, NGC 4303, one of our barred spiral galaxies, shown in Hubble and in the color image, and then our PA in the kind of purpley red image. Now, the first thing to notice in our PA is that there's not a lot of differences across this galaxy. It'd be really hard to tell where the spiral arms and the bar are if I hadn't highlighted them with the cyan and the pink contour. One of the main things we noticed when we looked at our PA in all of our galaxies is that it's pretty constant across different environments, across different galaxies, and seems to be really close to about 3.7 or 4, irregardless of where you look. With one major exception. We can see there's a lot of kind of dark purple holes across NGC 4303 that correspond to where those green contours are. The green contours, the lighter green contours, are showing us where the star-forming regions, or the H2 regions, are identified by the MUSE data. And so what we can see is that within those star-forming regions, within those stellar nurseries, ARPA drops. So ARPA is constant, except when you look in H2 regions, except when you look around sites of active star formation. That seems to be true across our sample. Here are 6 more of our galaxies. All 19 are in the paper, but they're hard to see in a small slideshow, where we can see ARPA constant, but we see these kind of dark purple sprinkles showing us where the H2 regions are, where we see ARPA drop. We think that's suggesting that within those H2 regions, PAHs are being destroyed by the higher intensity, higher energy radiation from young stars. Another way that we could show this is just by looking at the ionized gas fraction across all of our galaxies and seeing how ARPA changes as you go to regions dominated by ionized gas. So that's what this plot is showing. We can see if we take everything, including the H2 regions, including the star-forming regions, we see a drop-off in our PAH as we go to higher ionized gas fraction. Kind of for all of our galaxies, the different colored lines here, each of those is the binned median for a different galaxy, where the black cloud is all of our pixels from our sample. Now, if you take out the H2 regions, that decreasing trend goes away. That's the ARPA diffuse over there. That's if you don't have any of those star-forming regions. So that dip we see is really concentrated in those H2 regions, where the ionized gas fraction is highest and PAHs seem to be destroyed. If you ignore those though, if we ignore the H2 regions, like in that ARPA diffuse, ARPA is pretty constant. We're between 3 and 4 the entire time. This tells us that across our entire sample of galaxies, we seem to have a PAH mass fraction of around 5%, pretty similar to what's seen in the Milky Way, irregardless of where you look or what galaxy you look in. So that was kind of our first 2 major conclusions. ARPA is pretty constant, except in H2 regions where it decreases. So we wanted to say, okay, if we do take out the H2 regions, we said it was pretty constant, but is there anything that drives ARPA in one direction or the other? So we wanted to test, first of all, metallicity. This is something that we might expect lower metallicity regions to have lower ARPA values because they should have fewer PAHs. Lower metallicity, we kind of expect to have less PAHs. So we looked at whether or not, if we take out our H2 regions, does ARPA decrease as metallicity decreases? And for the most part, we found not really. We don't see a clear trend between ARPA and metallicity across our sample, although that's very likely because we don't have a lot of low metallicity galaxies in our sample of 19. The 2 lower metallicity galaxies we do have, NGC 5068 is that yellow line up there, IC 5332, which is the black line that does kind of go down a little bit. Maybe we see some signs of ARPA decreasing at the lower metallicity end, but we don't have a statistically significant sample to say so. The other thing we noticed is that there's a slight decreasing trend with ARPA as you go to regions of higher molecular gas fraction. So that F mole down there is just the surface density of H2 molecular hydrogen divided by the surface density of H2 plus H1. So the total gas mass, molecular gas mass divided by total gas mass. And we can see as we get closer to being dominated by molecular gas, ARPA decreases slightly for every galaxy in our sample, with the exception of our dwarf irregular NGC 5068. But for the most part, we do see this slight decreasing trend. That could be a sign that we're seeing PAHs coagulate into larger dust grains when we go into this really dense molecular gas, but we're not exactly sure, and this wasn't a super significant trend. So for the most part, we have all these beautiful maps of the PAH fraction made using JWST photometry for the 19 galaxies in the PHANGS sample. We are pretty certain that ARPA is a good tracer of the PAH fraction based on comparisons between our photometric measurements and dust models made using far infrared maps as well. And based on the maps of our PAH, we find that the PAH fraction across all 19 galaxies is pretty constant, with a value similar to what we see in the Milky Way, except for when we look inside of H2 regions where the PAH fraction drops due to photodestruction by the high energy radiation from young stars. If you want to see more of these maps, definitely check out the paper, and thank you for checking out this video.